Okay, so now we are on page, excuse me, I can't see the cursor. We are on page 46 of the textbook, and we're looking at the total for 36 children remembering up to 15 words, okay? And we've got this list here of 36 values. So what you do with something like this, the first thing you do is you simply count the values, all right? So there are 0 children who remembered 0 words, and there are 0 children who remembered 1 word. I think there's a 2 in here somewhere, right? Yes, there it is. There's a 2. So there's 1 child who remembered 2 words. And I think, oopsie. And now this you would write out yourself by hand, and it will be much easier to understand. There's 2 3s, so we will say 2 children remember 3 words. Okay. And so on and so forth. And when you do that, you end up with a chart that you can convert into a table. A chart like this. Okay, so you can say, okay, 1 child remembered 2 words, 2 children remembered 3 words, 3 children remembered 4 words, 4 children remembered 5 words, 5 children remembered 6 words. The highest number, the greatest value that was recalled was 7 words, and 6 children remembered that. And here's your distribution curve, right? So roughly 2/3 of the children will have remembered about that many words. Okay, that's your standard distribution around the mean. Okay, so once you have that, then you can go on to calculate how many children remembered how many words. Okay, the probability of a child remembering 9 words. What is the probability of a child remembering 9 words? Okay, we say, okay, how many times was 9 words remembered? 4 times, divided by the total of 36 possible outcomes. Okay, 4 over 36, which is 1 over 9, which is 0.11 or 11%. Then you can also calculate the possibility of a child remembering 9 or a number greater than 9, okay? And you would go up here and you would add up all of these. So it would be 4 plus 3 plus 2 plus 1, which is what? 7, 11, 12. 12 out of 36, so there's a 33% chance. Oh, my math is wrong. 4 plus 3 plus 2 plus 1 is 10, which is a 28% chance of remembering 9 or more. And that is the cumulative probability, and is the probability that a child's total could be equal to or greater than 9. Okay, so if we look here we go. This is the kind of thing that makes it so much easier to grasp. 1 word is represented by 1 block. So 2 words, 2 blocks, 3 words, 3 blocks. Now you can count. Okay, and you can actually just physically count how many children remembered this much. That is definitely going to be 10. All right. Okay, so that's a good way to see it. So it's the area under a curve, a probability distribution as an area under a curve. So now we're moving into curves. So we've looked at them as with discrete measurements like number of words remembered by children. But we're going to move now into continuous, where we're not actually measuring 1 plus 2 plus 3. It's the continuum between 0 and whatever the end of that scale is. Okay, and in that range, these are real numbers, and there's an infinite range of possibilities, just like there is in most of reality. Okay, so we're not just using integers, we're using real numbers. For example, age is a continuous variable. It goes down to the months, the seconds, and the fraction of a second. There's no limitation to how small it can be. It's a continuous line or an infinite number of dots. Okay, so here we were geeking out a bit. So the sampling space of ages, there's an infinite number of possible ages, okay? So the number of people that are 30 years old divided by the number of ages a person could be. But you can't divide by infinity. It's not a number, it's a concept. It's a thought experiment, okay? So we have to think about it with a different kind of math. And what we're going to do is we're going to range or interval of possibilities. So we're going to create intervals along that infinite line, or that interiorly is between 0 and 30. There's infinite numbers. So now we want to put intervals there, just like on a ruler. My ruler's not here. Okay, you'll have, there it is. So just like on a ruler, you'll go 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, even though there's an infinite number of points along this ruler. Okay, so we're going to make it easier for ourselves so that we can work with it. And what we can do is we can divide it into intervals and then use cumulative probabilities, okay, to calculate the probability of obtaining an outcome that falls in a particular range. And this is then the equivalent of calculating areas under a continuous curve. Okay, and who was telling me? This is the basis of differential equations. Not that we're doing anything that complicated. Okay, so now if we go back to figure 2.3, we'll see that it's perfectly symmetrical. It's a normal distribution. Okay, it's a normal distribution around the mean. Things are not going to be so perfect, but they are going to follow that pattern. Real data is rarely distributed in such perfectly symmetrical form, but it's of considerable theoretical importance. We expect a similar distribution whenever we make measurements on a continuous scale. Okay, it's a good model for many everyday variables. Many of the scores that we use are also clustered around the average and tail off towards the ends of the distribution. A normal curve. There it is. Okay, the normal curve. So it'll vary in its height, but the shape tends to be seen again and again and again because it tapers off in a symmetrical way. However, in real life, it's not going to be so smooth, but we'll expect the data to fit the normal curve. Okay, do you remember the Russian tail problem of the elections? Let's go and have a look again. Okay, that is not a normal distribution. You can see that there's something very wrong with those numbers. Welcome Donald Trump. Okay, not normal. Where's normal? Okay, I think normal is down here somewhere. Okay, that's a normal distribution in a fair election. So you can see that it's not there's very few things that are exactly on the curve, but when you look at the big picture, there's your normal distribution curve. It tells you that that is a fair election and everything is as it should be there. Okay. Okay, I'm going to end here and we'll continue in the next video. As you put in more and more and more and more numbers, that curve gets more and more and more smooth.